It is during the positive half cycle. There is no movement of holes and electrons. Barrier potential which is stopping the combination of the charges. An AC signal into a DC signal, which is greater, very much greater than the barrier potential. Hello students, this is SD Sir from the Temple of Excellence, Vidhyaashram, Pre-University, Mysuru. Continuing my discussion on semiconductor physics. Before that, we will have the thought for the day. If we are rich, we should always be polite. A plant bends down when it is ready to reap. So politeness, gentleness defines the behavior. So in my previous session, we understood what is meant by biasing a semiconductor. We studied the two types of biasing, what we call as forward biasing of a semiconductor and reverse biasing of a semiconductor. And finally, in detail, we understood what is the action of a semiconductor under reverse biased condition. In my today's class, I will discuss the action of a semiconductor when it is forward biased, and thereafterwards take a very, very important topic called rectification. So before that, we will understand the action of a semiconductor when it is forward biased. Now, to recall the meaning of something called as forward bias. So we saw if the p-type of the semiconductor is connected to the positive of the battery and n-type is connected to the negative of the battery. Andre, holes which are positive in nature is connected to the positive of the battery. Electrons which are negative is connected to negative of the battery. Same polarity is connected. That is what we call as forward biased condition. And there is a junction here which we say is the depletion region. Until and unless the depletion region is strong, there is no movement of holes and electrons. If the depletion region the so-called barrier potential is strong. Holes and electrons cannot recombine. Conduction is not possible. So we understand how a semiconductor works when it is forward biased. Now, when the diode is forward biased, so I am considering a condition where the given diode is forward biased. So when the diode is forward biased, the holes are repelled by the positive terminal. Same polarity, alva. Holes are positively charged, so they have to be repelled by the positive terminal, and electrons are repelled by the negative terminal of the battery. ಇದನ್ನ ನಾವು residue effect ಅಂತ ಕರಿತೀವಿ. So whenever a semiconductor is forward biased, holes are always repelled by the positive terminal and electrons are repelled by the negative terminal of the battery. As a result, bias voltage increases. ಇದನ್ನ external potential ಅಥವಾ external voltage ಅಂತಲೂ ಕರಿತೀವಿ. Because of the repulsion, bias voltage increases. The width of the depletion region and potential barrier decreases. Illenagutte, as you go on increasing the applied voltage, you learn this beautifully in the experiment. As the external applied voltage is increased, the so-called biased voltage is increased. That width of the depletion region, the so-called potential barrier decreases, and hence for an voltage slightly greater than the barrier potential which is stopping the combination of the charges, adike barrier potential. So when you apply an voltage, external voltage greater than barrier potential, holes and electrons move across. Andre depletion region completely dies. Depletion region is broken down and allows the current to pass through it. For any other increase in the bias voltage, the current increases sharply. What do I understand by this? To go to the physical meaning of the working, I will understand the IV characteristics of the curve. I andre current, V andre voltage anta artha. So this is the graph that will depict the working of a semiconductor when it is forward biased. So along x-axis, voltage is defined. Y-axis, current is defined in milliamps. You observe here, for a certain input voltage somewhere until here, there is no conduction at all. Gamansi Kavna. As I apply an external voltage, bias voltage, somewhere until this part of the curve, still there is no current. Why? That means the depletion region is still very strong. Barrier potential across this region is more than the applied voltage. So what happens? It is stopping the holes and the electrons moving each other. It stops the recombination of holes and electrons. ಈ ಕಾರಣಕ್ಕಾಗಿ ನೀವು ಎಕ್ಸ್ಟರ್ನಲ್ ವೋಲ್ಟೇಜ್ ಅಪ್ಲೈ ಮಾಡಿದ್ರು ಬ್ಯಾರಿಯರ್ ಪೊಟೆನ್ಷಿಯಲ್ ಜಾಸ್ತಿ ಇರೋದ್ರಿಂದ ಕರೆಂಟ್ ಕಾನ್ಸ್ಟಿಟ್ಯೂಟ್ ಆಗಲ್ಲ. Now, slightly increase the applied voltage, bias voltage. Now what happens? The width of the depletion region goes on decreasing, which means the barrier potential goes on decreasing. See, beautifully you can observe here. As you increase something called the bias voltage, more further, the strength of the depletion region, width of the depletion region goes on decreasing, barrier potential decreases. As a result, the holes and the electrons move towards each other. They recombine and a small amount of current is constituted. For one particular voltage, for one particular applied voltage, which is greater than barrier potential, one value of the applied voltage which is greater, very much greater than the barrier potential, the depletion region becomes very, very thin and there is sufficient conduction of current. And for any other bias voltage greater than barrier potential, there is a sharp increase in current. ಯಾವಾಗ ನಮ್ಮ bias potential ನೆನ್ಪಿಟ್ಕೊಳ್ಳಿ, bias potential ಅಂದ್ರೆ applied potential ಅಂತ ಅರ್ಥ. When the bias potential is greater than the barrier potential, depletion region is broken down. The width becomes very, very small. Holes and electrons freely combine. Conduction is seen. And if you further increase the bias voltage, there is sharp increase in the current. And this is exactly how a semiconductor diode works when it is forward biased. And this voltage, where there is a sharp increase in current, bias voltage for which there is a sharp increase in current, is what we call as knee voltage. ವಿ ಅಂತ ಕರಿತೀವಿ, ಅಥವಾ ಇದನ್ನ ಕಟ್ ಇನ್ ವೋಲ್ಟೇಜ್ ಅಂತಲೂ ಕರೀತಾರೆ. ನೀ ವೋಲ್ಟೇಜ್, ಬ್ಯೂಟಿಫುಲ್ ಟರ್ಮ್ ಅಲ್ವಾ? ವೇರ್ ದಿ ಕರ್ವ್ ಸಡನ್ಲಿ ರೈಸಸ್ ಅಪ್, ಅಂದ್ರೆ ಕರೆಂಟ್ suddenly exponentially increases. That applied voltage is what is called knee voltage. And here again there is some resistance to the flow of current, and that is called forward resistance. So we have studied what is forward resistance. Small resistance to the flow of current when the diode is forward biased is forward resistance. Knee voltage, bias voltage where the current increases rapidly. And few uses of junction diode. Very importantly, it is used as a rectifier and it is used as a switch. Now, when I mentioned the uses of a PN junction diode, I told it mainly works as a rectifier. ಹಾಗಿದ್ರೆ what is a rectifier? What is this entire process of rectification? Very beautiful. Exam al matra ಖಡಾಖಂಡಿತವಾಗಿ ಕೇಳೋ ಪ್ರಶ್ನೆಗಳಲ್ಲಿ ಒಂದು 2020 ಪೇಪರ್ ಅಲ್ಲೂ ಕೇಳಿದ್ದಾರೆ, rectification. So this is a very important 1 mark question, something that we discuss about rectification. It is a whole process of converting an AC signal to a DC signal. My dear friends, please to remember the process of converting an AC signal into a DC signal is what we call as rectification. Then what is a rectifier? It has to be a device like a junction diode which will convert AC to DC. Nodi, rectification andre it is a process. What are we doing in this process? We are converting an AC signal into a DC signal. And a device like a PN junction diode, which converts AC to DC, is called as rectifier. And we have two types of rectifications. One is called a half wave rectifier. The other one is called full wave rectifier. What happens in a half wave rectifier? As the name itself says, only half cycles of AC is converted to DC. ಅತ್ಯಧಿಕ ಪ್ರಮಾಣದಲ್ಲಿ AC-ನ DC ಕನ್ವರ್ಟ್ ಮಾಡಲ್ಲ ಹಾಫ್ ವೇವ್ ರೆಕ್ಟಿಫೈಯರ್. ಕೆಲವೊಂದು ಸೈಕಲ್ಗಳಲ್ಲಿ ಮಾತ್ರ AC DC ಕನ್ವರ್ಟ್ ಆಗುತ್ತೆ. ಓನ್ಲಿ ಹಾಫ್ cycles of AC is converted to DC. That is called half wave rectification. And as the name itself says, full wave rectification, both the cycles, positive half cycle as well as negative half cycle, is converted to DC. So, what is rectification, students? It is a process of converting an AC signal into DC signal. What is rectifier? A device which converts an AC signal to DC is called rectifier. Half wave rectifier, only one half cycle of AC is converted into DC here. Full wave rectifier, it converts both the cycles of AC to DC, hence it is called full wave rectification. And therefore, now we will understand the working of a half wave rectifier. 5 ಅಂಕಗಳಿಗೆ ಯಾವಾಗಲೂ ಕೇಳುವಂತ ಒಂದು ಪ್ರಶ್ನೆ, half wave rectifier. So this is the circuit which shows the arrangement for half wave rectification. And this is the symbol for a transformer. So symbol for a transformer, AC chapter ಅಲ್ಲಿ ಡಿಸ್ಕಸ್ ಮಾಡಿದ್ದೀನಿ. ಸ್ಟೆಪ್ ಅಪ್ ಟ್ರಾನ್ಸ್ಫಾರ್ಮರ್ ಆಗಿರಬಹುದು, ಸ್ಟೆಪ್ ಡೌನ್ ಟ್ರಾನ್ಸ್ಫಾರ್ಮರ್ ಆಗಿರಬಹುದು. ಸೊ ದಿಸ್ ಈಸ್ a transformer. Now note, any AC signal that has to be converted as DC is fed as an input to the transformer. Nodi, AC symbol ide illi. So the AC signal which has to be converted as a transformer is fed here. Converted as the DC is fed to the transformer. This is the junction diode which is used for rectification, and this is called the load resistor across which we are measuring the output. So, input AC to be rectified is fed to the transformer, and the rectified DC is measured across the load resistor. Now, during the positive half cycle of the input, the point A is positive with respect to B, and hence the diode is said to be forward biased. Current flows through the load resistance from M to N. Now, what is that I am trying to explain here is, this is the positive half cycle and the negative half cycle of the AC. When the positive half cycle is reaching the transformer, yavaga positive half cycle is reaching the transformer, the end A is positive and this end B is negative. Nenpitkoli, it is during the positive half cycle. Only when this positive half cycle is reaching the transformer, end A becomes positive, end A becomes negative, which means now the diode is forward biased. And as you studied before, when it is forward biased, there is conduction. The current flows through the load resistor. It is measured output here and it is rectified. But during negative half cycle, the point A is negative with respect to B. Diode is reverse biased and no current flows from M to N, which means when the negative half cycle is reaching the transformer, A becomes negative, B becomes positive, which means now the diode is reverse biased, no conduction is happening, no output is measured. See, very beautiful. Only during the positive half cycle, the diode is forward biased and the output is a rectified DC. But when it is the negative cycle is reaching the transformer, diode is reverse biased and no conduction happens. Which means the diode allows only positive half cycles to flow through the load resistor and to be rectified. So clearly we have this circuit diagram here. So if you observe the output waveform, it is something only like this. You can see the negative half cycles are absent. Only positive half cycles are present. Only positive half cycles are rectified. And this is what is called as full half wave rectification. So students, in today's class, we learned the action of a diode when it is forward biased. We learned what is rectification and the action of a diode as a half-wave rectifier. Only positive half cycles getting rectified. Why? Only for a positive half cycle, diode is forward biased and conduction happens. The next class, I'll come up with the reverse biased. And with that, we study full wave rectification. Until then, have a nice time. Thank you.